So we discussed some special orbit closures, and I told you the classification of orbit closures is still open. Even for Takemura curves, we don't know how to completely classify them. Nevertheless, recently there was a fundamental result that tells us the structure of all these orbit closures. Even without a classification, we can still see how they look like. So this is a theorem due to Eskin, Merzek, Harney, and Mohammadi. So they wrote two papers, one by Eskin Mazharni, the other one by the three authors. So this is also like one of the important parts of Mazharni's field medal work. So who won the field medal in Korea 4 years ago. Okay. So let me tell you the statement. So it says the following. So any orbit closure, it doesn't matter if it's a Takemura curve or some intermediate subspace of H mu, any orbit closure, although we don't know how it looks like, the dimension or whatever, any orbit closure, and keep in mind this orbit closure is only an analytic closure so far, okay? Is called let me write down the terms I'll explain in more detail. Is a affine invariant submanifold. Okay, so maybe let's emphasize it. For short, I'll just call it AIM, okay? What does this mean? i.e., this invariant just comes from this invariant orbit, GL2R. This affine means locally it looks like a vector space. This means an affine space, okay? That is, it is locally linear. And although if I write down locally linear, still not so clear what do I mean. So let me further explain. This locally linear means cut out. Maybe I should say closure in H mu. So I have a subset in a total space. And on the space H mu, I have local period coordinates. I use this period coordinate as my local coordinates. When I say that locally linear, just means this subset is a locally linear subspace of H mu, when I've used a local period coordinates as a basis of the neighborhood, or the tangent space of H mu. Okay. Real linear equations of period coordinates. And these linear equations are also special. They have real coefficients. Okay. So my space H mu is a complex manifold, right? These period coordinates are complex numbers. Okay. And this says, okay, so any orbit closure is locally a linear subspace cut out by real linear equations of period coordinates. Okay. So the result is really deep. So the paper actually by Eskin Mazharni is 250 pages long, and I think they got one referee report. Even the referee report is 42 pages long. It took them, especially actually the paper was published after Mazharni passed away, so I think it took them like a long time to revise the paper. But eventually, so now it's published. And another more recent result was done by a student of Eskin, which is also important. This is by Simeon Philip. And built on this EMM result, it tells us we can actually replace these real coefficients by algebraic numbers with any orbit closure. Actually, he's defined over number fields. In particular, they are. So I emphasized it earlier when I take the object closure, it is under the analytic topology by period coordinates. Now they are defined over number fields. Actually, they are quasi-projective varieties. In other words, you can just take the series closure. It's the same as taking the analytic closure, but it's not obvious. It's just guaranteed by the Phillips theorem. So these object closures. So now I call it affine manifolds. Are algebraic varieties. So that is taking this analytic closure is the same as taking the series closure. So recall the action is GL2R action, right? There's no reason to believe it is really algebraic, right? But this is just followed from these two fundamental theorems. Okay. Right. So this serves as a basic introduction to the subject technical dynamics. Okay. Usually when I give this talk, so the first half hour I will just said what I say here, but it took me more than 3 hours here. It's okay. But from now on, I'll specialize to something more algebraic and some of like my recent work. Okay. So I plan to focus on two things depending on time. So maybe I can only say one thing. Let me start from this term affine invariant manifold. Okay. So when I wrote down this survey paper Yunnan mentioned, so I introduced this term affine invariant manifold. I had to emphasize this term affine in the sense that it's not an affine variety. It is locally linear, like an affine vector space. But then I wonder, so from the viewpoint of geometry, whether these affine invariant manifold actually are in the sense as a variety of affine varieties. So let me pose the following interesting question. Affine invariant manifold affine. Here affine means as affine varieties. Okay. So maybe let's first recall the definition of what is affine variety. You should think of affine variety like in two ways. Maybe in an elementary way, these are like defined polynomial equations inside the affine space. But there's a more formal way to say it. Affine variety, let's call it V. So actually, you can always write it as a complement of a hypersurface in the projective variety. Let me write it this way: x minus h, where x is a projective variety and h is, because x is projective, that means you can put x inside the project space, right? If you have a project space, then you can take a hyperplane, and h is a hyperplane section. So the picture looks like I can put X in a project space, say some project space Pn, and I have X here. I should draw X as some arbitrary varieties. X, so I take a hyperplane H to cut out something and look at the complement away from H, the complement X minus H. That is affine variety V. And put it formally, so a hyperplane section is nothing but a very ample divisor, right? Because by definition, very ample divisor means you can use H to induce an embedding of X in the project space. So in other words, in short, so V is equals X minus like a very ample divisor. Okay. So in other words, the complement of a very ample divisor is the affine variety. Okay, so that's the definition. Okay. So why do you want to study affine varieties? I mean, as you know, if you studied geometry before, you can use affine varieties as a sort of a local charts to glue together to form a projective variety. And they also have simple structures. For example, if you take affine variety, the affine variety does not contain any complete algebraic curve. So one remarks that the affine variety does not contain any complete algebraic curves. Well, that is quite clear from the definition. If I had a complete curve, so for example, Riemann surface without puncture, contained in the affine variety V, then I put everything in the project space. That curve must intersect this hyperplane H because H is very ample. But because V is a complement, so I have to remove the intersection point from C. That tells us C inside V cannot be complete. So there's no complete non-trivial varieties contained in an affine variety. So what are some examples of affine variety? For example, if you take a vector space, it's certainly affine. Like that is away from a hyperplane in a project space. You can also take a complete curve, algebraic curve, minus a non-empty set of points, right? Minus say P1 up to Pn. This is also affine. Because you can always take a linear combination of these points to make the total degree arbitrary high to give you a very ample divisor, so that the complement becomes affine. Okay. These are clear. Okay, so let me try to convince you that this question is not a crazy question. It has some evidence to be possibly true. I don't have many examples of affine Euler manifolds, right? That depends on this, how I know the object closure. At least I have introduced Tech-Mirror curve, right? Let me just say one remark. It's a quite easy remark. So Tech-Mirror curves are always affine. So the question is true for Tech-Mirror curves. Why is it? Well, it's because, look, what is a Tech-Mirror curve? Or in general, I claim, well, Tech-Mirror curves, they come from just the orbits themselves without taking the closure. Right? So if I take a flat surface representing a Tech-Mirror curve, that generates a Tech-Mirror curve, and take some polygon picture. Okay? So suppose I apply this action to generate a Tech-Mirror curve. Oh, I can always pick some special element A inside this GL2R to make some edge of this polygon arbitrarily short. Sometimes maybe rotate it to and then shrink, like do a shrink on one direction to make some edge I chose an arbitrary short. But if I choose this edge to be arbitrary short, so in the end, that will make the surface like a break. That means the underlying surface may degenerate, cannot be a smooth Riemann surface anymore. In other words, if I take the closure of the Takemura curve in the modular space mg bar, so the closure of the Takemura curve always meet the boundary of mg bar non-empty, because in the end the surface will break. That makes like must be some nodal Riemann surface. In other words, the closure, this just comes from, so the closure of Takemura curves. So here's the closure I'm taking inside mg bar. In mg bar, the Riemann space must meet the boundary of mg bar by using the shortening one special edge so that it makes the surface break. That tells us if I consider the original Takemura curve without taking the closure, there must be some like a point, a miss coming from the boundary of mg bar. But I just said that if you take a complete curve minus some boundary points, the remaining part, the complement is alpha. That tells us Takemura curves must be alpha. In other words, Takemura curves cannot be a complete curve sitting inside mg. It always meets the boundary of mg bar, because I can make the surface break by applying some special GR2 action.
H-mu is not compact.
H-mu is not compact, but non-compact space may still contain compact curve. Yes. Yes, I'll give you some example. I mean, for example, I can take P2 minus a point, then it still contains a P1. That's okay, right? I'll take CP2 minus a point.
And the compactification of H-mu is if you have this boundary point.
Say it again.
So for example, if you have some compactification of H-mu, and then you consider that this affine invariant curve meet maybe this the limit of this.
Okay.
And we consider that this compactification of modular curve, and then consider that this Hashimura curve, limit of Hashimura.
Yes.
Just matching. I mean, when you consider the compactification of H-mu with the compactification of mg bar.
I guess I see your meaning of the question. Okay, so maybe, so I can ask this question in two ways. So usually to me, I consider everything mod this C-star action. So I already rescaled. I can projective everything. So in other words, all I'm seeing is that the underlying Riemann surface, no matter it's parameterized in the Takemura curve or parameterized with differential, may become singular. So in any case, it cannot live in the strata or the modular space parameterized in smooth curves only. That just tells me the Takemura curve, no matter you think of from which viewpoint, in strata or in the modular space, cannot be complete. Yeah. So maybe, yeah, I usually want to consider maybe, okay, so the Takemura curves are not quite just the orbit, is orbit modulo the C stars, right? But to me, from now on, maybe it's better to think of like everything modulo the C star. So when I see Hodge bundle, I mean the projective-wise Hodge bundle. When I see the strata H-mu, maybe I want to modulo the C star action by rescaling the differentials. So when I consider the modular space, actually I forget the rescaling of the differential information. It does not really matter, it's just notation convenience to us. For example, if you want to study a vector space, usually you projective-wise and consider the projective space instead. But to your question is that if you want to compactify the space, so first I want to projectivize it, then I compactify it. So, yes. Yeah. So that, if I had time, I'll talk about compactification later, but not today. Okay. Any other questions? Another affine manifold you can cook up is similar from this branch cover construction. I said for Takemura curves, this construction is by using just only one branch point, right? if I impose more branch points, then I will get a higher dimensional Hurry space because I can move the position of these branch points in the James 1 curve. Suppose I have n branch points, then my target space will be the James 1 curve with n markings, that is n1n, which is an n-dimensional space. Similarly, I have another example. I can consider Hurry space of torus covers with n branch points. So this gives you an n-dimensional orbit closure. Again, so here modulo C star. Otherwise, if you rescale the differential, it would be n plus 1 dimensional, but let's modulo C star. Again, so you have this branch cover with n branch point. You can still take dz and pull it back. Once you specify the ramification type over each branch point, you still get into some strata. But just because you have n branch point, when they vary, this GL2 action not only changing the torus, but also changing the position of the endpoints. You have to take all of them into account. You will get the Hurry space sitting over M1n, so the Hurry space is n-dimensional. Okay. But these are still orbit closures of n dimension. The same reasoning works. So the covering is exchangeable with this GL2 action. So these are n-dimensional orbit closures, modulo C star. So these are a claim. So these Hurry spaces are also affine. Okay. Affine varieties. The reason is because of the following. So all I need to do is this. Let's give it a name. I call it H. Yeah. Let's do H. Yeah. So let's just call it H. This is because I have this Hurry space here mapped to M1n, right? So this is finite. It's a finite morphism. Again, so when you specify a James 1 curve with a fixed n branch points, there exists only finite many non-isomorphic covers. So this is finite. And you can show that if I have finite morphism, then if the base is affine, the upstairs is also affine, because I have some kind of complication where this is a complement of very ample divisor. I have a very ample divisor pull back from a finite morphism, still get something by ample. So affinity is preserved under finite morphism. So indeed, you can only show that. So this follows from this is because this base variety M1n, you can show that is affine. Yeah. This is not too hard to show. You can just James 1 with n markings, you can just prove it directly. And different ways to prove it. So once you know this is affine, then all the finite coverings becomes affine. These are some easy remarks. So this known branch cover construction related orbit closures, they are affine. Okay, they are not complete. They are affine. Then the question is, we don't have a classification of all orbit closures. How do we study this question? So if you give me one, then maybe I can look at it and study it. But we don't know how many other. Maybe there are many, many different ones. So let me remark one more thing. So if you believe the answer to the question is true, then you only need to check for the strata. You don't have to check for each individual orbit closure contains the strata. There's one other remark. So if, and put this way, if in general, if V is an affine variety, then any Zariski closed subset in V is also affine. That actually is a standard fact in Arab geometry. For example, you can find the proof in Mumford's Red Book. So if your ambient variety is affine, now you take a closed subset in V, then this closed subset remains to be affine. That tells us if I can show the stratum H mu itself is affine, then plus I know by asking Mazahani, Mohammadi, and Phillips result, now I know all these affine manifolds, they are closed, Zariski closed subset in the strata. Because I told you, taking the identity closure is equal to taking the Zariski closure by their result. So So if I know furthermore the ambient space H mu is alpha, then any closed subset in H mu is alpha, including all these alpha neural manifold because they are closed subset. Okay. So let me say it this way. So the question boils down to study whether each stratum H mu is alpha. Okay. So that tells us so if H mu is alpha variety, then so all alpha invariant manifolds in H mu are also alpha. Just by this remark. So we have reduced the study to the ambient stratum H mu. So I checked a few low genus strata. So let me maybe do one thing. So again, so some I will be more precise. Some low genus strata. They are alpha varieties. So another thing I'm going to tell you is that, so I told you, when I say strata, I do mean the strata kinetic component, right? Sometimes the strata has more than one component. So then it just means I want to take one component, ask whether that component is alpha. So if it has more component, I told you there are two structures, right? The spin structure and the hyperelliptic structure. So for all hyperelliptic components, they are alpha, even for high genus. So all hyperelliptic strata components, they are alpha. Okay, maybe let me explain the second part. In your low genus strata is just case by case. You have to examine. You use some low genus curves geometry. So the hyperelliptic strata actually is for all genus, but I need this hyperelliptic structure. Well, this essentially relates to the following thing, almost equivalent to the following. So what is a hyperelliptic curve? Let's recall, the hyperelliptic curve means x admits a 2-to-1 cover to P1, right? And also, if x is of genus G, so this double cover is uniquely determined by choosing 2G plus 2 branch points in P1. So in order to say a hybrid curve of genus G is equivalent to specify 2G plus 2 points in P1, right? So I have 2G plus 2 branch points, Q1 up to Q, 2G plus 2, these are branch points. Okay. And this hybrid strata is essentially just governed by the following data. There may be still some finite morphism depending on what kind of zero you want to pick. But in the end, you basically boils down to show that you have P1 with a bunch of marked points. That modular space is alpha. That is the modular space, if you think of it this way, the modular space M0, say 2G plus 2, right? The genus 0 curve with 2G plus 2 distinct points. But again, this is very easy, right? You have P1. P1 has no non-trivial moduli. You take a bunch of points, and then the modular space just looks like some bigger project space minus some hypersurfaces when the points meet. So this certainly is alpha. There's no doubt. It just looks like a project space minus a bunch of hypersurfaces corresponding to when the branch points meet. And then essentially using this, you can show that all hyperelliptic strata components are alpha. So we have some evidence in low genus and for the hybrid cases. But besides these two special cases, I really don't know whether for other strata in high genus, whether they are alpha or not. I mean, it's not a very difficult, well, so first of all, I don't really know the answer, should be yes or no. But if you try some strata in genus 4, and even in some strata in genus 3, you might get something. So if you're interested, you may want to start just trying this low genus geometry to see whether you can get this affinity or not, just for the strata. Okay. But let me just say one more thing related to the study. So I remarked earlier, if you have an alpha variety, then it does not contain any complete curve, right? So conversely, if you believe the answer is negative, so for example, you can go finding a complete curve contained in a strata. Because if I know h mu contains a complete every curve, that immediately tells me it's not affine. So my question has a negative answer, I'm done. So that means if you believe the answer is no, then you may want to find a complete curve. So another remark is that, so if there exists, maybe let's put in h mu contains a complete curve, complete accurate curve, then h mu is not affine. Okay. Well, so you want to study this question, maybe this related question, like complete curves or complete subvarieties containing h mu. Let's first come back to the situation of the modular space Mg. Because h mu carries more information, it's like inside the Hodge bundle, parameterizing the curves and differentials. You may ask, what is the situation for Mg? Mg is also not complete. I'm not taking Mg bar, the smooth curves only. And whether there are complete varieties, complete curves in Mg, right? That's the first question you may want to think. And then you maybe use some techniques and to develop some analog for this related space h mu. So let's first recall the study for complete curve inside Mg. That's actually in general complete subvarieties in Mg. The modular space are smooth density curves. Okay. So let me only mention maybe like two results. So one is due to DRs. This was also done like more than 30 years ago. So I think DRs was the first student of Joe Harris in the early 80s. It said the following. So any complete subvariety in Mg well, has dimension, complex dimension bounded above by G minus 2. It does not say they do not exist, but if they exist, there is an upper bound for the dimension. It cannot be too high. Otherwise, if it's bigger than this, it cannot be complete. Well, let's take some low genus example to take a look. So for example, if genus is equal to 2, that tells us there's no complete curve, right? 2 minus 2 is 0. But M2 is a hyperelliptic curve. I just told you they are affine, right? M2, genus 2 curves are all hyperelliptic. Clearly, yeah, if you believe this locus of hyperelliptic curves is affine, the M2 is affine variety. There's no complete curve. So that's clear. Let's go to M3. And it says M3 may contain complete curve, right? Cannot have a complete surface. Right? 3 minus 2 is 1. So this bound actually is sharp for M3. Okay. So I'll also quickly discuss how to find the complete curve in M3, or in general for genus bigger than or equal to 3. So maybe say in M3, or in general Mg for genus bigger than or equal to 3, there does exist complete curves, algebraic curves. Okay. Okay. The reason, well, there are different constructions. So one abstract way to find this complete curve is the following. So you can take M3, or actually Mg, let's assume this. Take Mg and embed inside the modular space of principally polarized abelian varieties. So this is a PPAV. There's some kind of modular space of abelian varieties. So what is this map? You take a curve and you associate with the Jacobian of this curve. So if C is a genus G curve, the Jacobian gives you a G-dimensional abelian variety. Okay. And there are other abelian varieties in general not coming from Jacobian, but at least this gives you embedding that by the Torricelli theorem, different Jacobian distinguish different curves. Okay. Now AG has many, many different complifications. You take one complication, I won't tell you how to construct this complication, but there's one complication that's called the Sazek complication. So that means there is some special complication of AG, where I look at under this complication, how does the image of Mg look like? under this complication. So Satake complication. So the closure, let's call it mg star of mg. So star denotes Satake complication. Closure actually has boundary of codimension bigger than or equal to 2. So here I'm using genus at least 3. If genus 2, then it does not work. So in other words, let's forget what Satake complication is. All it says that you can find some complication. So suppose I have some interiors of like this is mg, and I can compactify it so that mg bar looks like I have some boundary, and this boundary is of higher codimension. This is the boundary of the codimension inside this complication is bigger than or equal to 2. Okay. The complex codimension, okay? Then it tells us if I have some codimension 2 or higher subvarieties inside this compactified variety, and everything is still projective, this complication. I can take some very ample like divisors, let's call it A. Not use A here, let's call it L. In mg star, such that if I raise to the intersection, let's do this way, very ample divisors. Sorry, let's call it D1 up to D. The total dimension of mg is 3g minus 3, so I'll take 3g minus 4, so that I can make the intersection to be a curve, and this curve can avoid any given codimension 2 or higher subvarieties. Such that, so the intersection of these very ample divisors minus 4 is some curve, say a curve, such that C and the boundary are disjoint. So here I'm using the boundary has higher codimension. If the boundary is codimension 1, I may not be able to do it. Okay. But if I have this complete curve away from the boundary, that means it really contains the interior. Right? So that tells us C is a complete curve in the interior of the modular space in mg. Okay. So this is a general strategy. If you have a space, and if you like a not complete space, you compactify it so that the boundary remains to be projective, and the boundary is of codimension 2 or higher. Then that guarantees you will find a complete curve inside it. So this gives you the abstract construction for complete curves for any mg as long as genus is bigger than or equals to 3. Okay. And that also tells us the bound, DR's bound, for genus equals to 3 is sharp, because it tells 3 minus 2 is 1. I do have complete curves. What is the next case if I take genus 4? So DR's bound tells us there may exist a complete algebraic surface, right? Let's go to the next case. Well, unfortunately, even in M4, so we actually don't know whether there exists a complete surface. That's an open question. Exists a complete surface. Okay. This sounds embarrassing because 4 is still very low genus. But it has been a hard question just to construct a complete algebraic surface sitting inside the modular space genus 4 smooth curves. So this is 3 times 4 minus 3 is a 9-dimensional variety. You want to find a complete surface inside it. But so far nobody knows the answer. So, okay. So in other words, this Diaz bound, nobody knows in higher G's whether it's sharp or not. So the actual complete subvarieties you construct always has much lower dimension compared to Diaz bound. But on the other hand, we don't know how to improve this bound. So it's unclear. So the true bound for general G. Okay. So that's actually all we know about complete subvariety inside MG. So there's not much development since Diaz results. There are some new proofs by other people. Still, they all got the same bound. Yeah. Okay. All right. So let's come back to the case of strata. Okay. All right. Any question?
But in the complete, in this remark, you said whether there is a complete curve in a closed orbit. Is there a similar method of the Teichmüller curves? Does not work? For example, projecting to MG and then try to meet the MG bound?
Well, I mean, there already takes the orbit closure, right? And Teichmüller curves itself somehow it is equal to its closure, right?
Right, because maybe it can be coming from just closure.
Right. In other words, any orbit is not complete, but the orbit closures could complete because orbit closures already. But in general, orbit closure is not equal to an orbit unless it's a Teichmüller curve. Right? Yes, any orbit itself before it takes a closure cannot be complete, but orbit closure certainly could be complete. It gives you more points, right? You don't know. All right, so I'm going to tell you some results I know, but I need to generalize this setting of the strata a little bit. That also has a relation to this complication of strata business. Hopefully I'll mention it tomorrow. Okay, so let's come back to this differential case. Now I want to enlarge our study to include not only holomorphic differentials. Right? When I say differentials, so far I have only concentrated on the case where the differential is holomorphic. In other words, the associated canonical divisor is effective. Right? But now I want to consider possibly like a meromorphic differential as well. In other words, I can consider meromorphic section of the canonical line bundle. That's okay. Let's actually enlarge our study. Let's consider mu from now on. 1, I still use the same notation as a partition of 2g minus 2, such that some mi can be like smaller than or equal to 0. Okay. But still I require the sum is 2g minus 2. If mi is negative, that means I'll have some pole of certain order given by the absolute value of mi. Okay, so let's use the same notation h mu. And with some mi could be negative, could be the space of x omega, so that omega now I cannot write down the 0 only, right? I should write down something like this: 0 minus the pole divisor, right, is equal to m1p1 plus mmPn. That is, omega has 0 and pole if some mi's are negative of type given by mu. Okay. Okay. So you may wonder, so I have this polygon presentation for the holomorphic differential. But now if I have a pole, is there any similar polygon presentation for the meromorphic differential? Actually there is. So let me show you an example. But it won't be a polygon. It will be like some kind of in some generalized polygon of infinite area. It's not finite. Where the poles will sit at infinity. So there is like maybe sort of like a polygon, not quite polygon, but let's just polygon of infinite area. Okay. So that corresponds to meromorphic differentials. Now let's do an example. So let's do one example. This is, if I can do it, okay. So let me take, again, so a parallelogram, okay, in the Euclidean plane, okay. If I take the interior parallelogram and glue the edges, you get a flat torus. Now I do the opposite. I take the complement of the parallelogram, look at the outside. So this is my surface. This part is empty, I remove it. I still glue the edges this way. These are glued together, but I look at the outside. And at a point at infinity, let's call there's a point P at infinity. So at a point at infinity, at least topologically, you still get a closed surface. Okay, you just wrap up at infinity, and this side, you wrap up here, there, still get a closed surface. And I still have the flat structure, right? Everywhere is flat. I have some special points here, right? Because these are glued, you can check these four vertices are still together, that's called Q. Okay? And what is the angle at Q? Now you have to count outward, right? Because I'm taking my surface outside. Outward you will get at Q, the angle is, you have altogether 8 pi minus 2 pi 6 pi. That is still 2 pi times 3. And that is, by the formula, that is 2 plus 1. That tells us the corresponding differential at Q, you'll still get a double zero, right? That's fine. At Q has nothing to do with infinity. So locally, still everything is finite. Okay. So that has Q is a double zero of some differential. Of a differential. I only need to tell you how P looks like for this differential omega, right? I claim P must be a double pole. In other words, this omega is meromorphic differential with a double zero at Q and double pole at infinity. And the underlying surface, topologically, is still torus, is genus 1. That you can check again by Euler characteristic. But this differential thing, you have to read off the correct order. So since omega, I claim, has a double pole at infinity, labeled by P. Okay, how do you think of it? Why is this kind of like one Euclidean plane at infinity, it gives you a double pole? So what is a double pole look like under local coordinate? Double pole means I have, maybe write it here. So a double pole locally is something like 1 up to some constant 1 over z square dz, right? So I have my differential form, certainly at the origin I have a double pole. Okay. Now think about this. If I take a disk, okay, and just take the differential, let's call it d, maybe x, and here I take my origin, and dx is no variation. Okay. Now I make a change of coordinate. I want to give you a coordinate at infinity. The standard way to do it, I change x to its reciprocal, right? Let's let z becomes 1 over x. So if you use that coordinate, when z is 0, I mean you have to flip the disk outside, right? So under the z coordinate, so suddenly this thing flips to infinity, right? Then you just look like over for z, you just get like outside, right? If I do the z coordinate, right? When x is 0, suddenly z becomes infinity, right? This is the z coordinate, this is the x coordinate. Then if I do z equal to 1 over x, dx becomes just d of 1 over x, right? That is, up your sun is just negative 1 over x squared dx, right? That means I flip this flat disk. Now it becomes a complement. Right? And now the origin goes to the infinity, and suddenly I just get a form with a double pole at infinity. And that's exactly the expression here. Right? And if you have a higher order pole, then you can first take like some copies of flat disks, but you need more copies, and then flip each of them. In other words, higher order pole, you need more than one copy of this Euclidean plane, but you have to decompose it into not half disks, like half planes. And these edges, I showed you in my first lecture how to glue consecutively will become some half planes, and you glue like consecutively. This one goes to the next one and go around. And all the infinite points in this picture will glue to be the same pole. You have more copies of the planes, will give you a higher order pole. Here for a double pole, you only need one plane. For triple pole, you need two planes, yes, and so on and so forth. It's just by flipping the corresponding disks.
So the compactification of infinite point is P1, so you have a double zero, then you should have a double pole.
This is elliptic curve, so it has to be not P1. This is, yes, because elliptic curve, you have the canonical bundle trivial of degree 0.
Yes, but when you compactify as the infinite point on the plane, it's P1.
Oh yeah, just without this part. If you only have Euclidean plane with a point, you get P1 with yes, that is just 1 over z squared dz.
So then order of a pole should be the same as the order of the zero at the
differ by 2, right? Because I have a 0, I have an ordinary point, which if I flip, give me a double pole, right? So here, this is a 0 of order 0, which I get a pole of order 2. If I have a 0 of order 1, if I flip it, I would get a pole of order 3. Because of you can just do this calculation. Okay, that basically tells us if you know how to represent like a 0 of certain type, you just use its reciprocal, you know how to flip the flat disks, you just get infinite half planes and glue them together. But the things that are showed by these examples, if you have a pole, that certainly means your, your flat surface will be of infinite area. Right? You must go to infinity. Right? In other words, if you integrate something like omega wedge, omega bar at the pole, you wouldn't find a finite number. It just does not converge. But that's okay. So that's one motivation to consider differential with pole. Another thing is maybe since I already brought up this picture, let me do one more example. I will maybe come back to this example tomorrow when I talk about compactification. Sorry, just do this. So actually, let me indeed just tell you the result I know first before I talk about this compactification thing. So here, let me write down theorem. So I sort of explained this Meromov differentials also makes sense, right? So the theorem, so I did it like about a year ago, so last summer. So it said the following. So suppose mu, again, is a partition of 2d minus 2. Such that at least one entry mi is negative. In other words, I really consider like strictly meromorphic differentials. If you give me a holomorphic differential with all positive zeros, I don't know how to do it. But if you give me one pole, at least one pole, so then the modular space of this type of meromorphic differentials. So this means, i.e., the differential I consider meromorphic differentials. Okay, so there is some pole, okay? Then the space of meromorphic differentials, H mu does not contain any complete curve. Okay. In other words, the strata of meromorphic differentials, they have no complete curve. So that gives you another evidence about this affinity. Still, I don't know whether these are affine, but at least there's no complete curve inside. This is already a little surprising to me when I found this, and also when I see the proof tomorrow, you'll see where I use this condition. I do really need some negative number to show up because I have to compare two signs. I need positive and negative to get some contradiction if there's a complete curve. Okay. Tomorrow, I think I will present the proof. It's not too long, and it only uses essentially one non-trivial fact about some positivity lamp bundles on the modular space of curves. So that I will use. Other than that, it's some basic calculation on the universal curve. And then tomorrow I'll also come back to this picture to explain another context. So this meromorphic differentials really shows up when you consider holomorphic differentials when they degenerate. You will see some meromorphic differentials to show up. That will give us information how to compactify the strata of holomorphic differentials. The boundary you will see some reducible curve, like nodal curve, where on some part of the nodal curve, the differential actually become meromorphic. Yeah, so it's natural. Okay, I think I'll stop here for today.